Before there was Einstein, we had Newtonian physics. And in Newtonian physics, we explained physical events happening in space with time being a separate parameter. This was a successful construction for a long period of time. However, once Einstein came into the picture, we realized that time is not something separate from the space coordinates. In fact, time is relative and very much dependent on the space coordinates. Therefore, it became very necessary to combine time as a coordinate and space together to describe physical events. An attempt to create this kind of a construction of space-time was provided by Minkowski, where he combined one space and one time coordinate into space-time. Now, this kind of a space-time is very different from our usual space containing, let's suppose, x and y coordinates. In this video, I'm only going to be looking at 2D diagrams because that's easier to draw on a board. The beauty of space-time diagrams is that using very simple intuitive constructions, we can explain some of the bizarre consequences of relativity like time dilation, length contraction, Doppler shift, velocity additions, etc., just by looking at space-time diagrams. However, to do that, we need to understand the space-time construction is slightly different from normal Euclidean space. In my coming lectures, I'm going to demonstrate how various phenomena like time dilation, etc. can be easily shown or proven from the geometry of space-time. But before we do that, I want to make today's video in which I show some very simple and basic differences between the calculations that we usually do in Euclidean space and the calculations that we are going to do in space-time. These are very simple and yet interesting differences that once you get to know, after that, calculations in space-time geometry will become very, very easy for you. So let us start today's lecture. So we're going to start with the very obvious difference that arises from the space-time interval. So in Euclidean space, let's suppose we have a 2D plane containing x and y axis. I want to find out the distance between any two given points. So I have 2 points, let's suppose P and Q. Alright, so I have 2 points P and Q, and I want to find out the length of this line segment, you can say, or this vector. Alright, so I want to find the length of this PQ. I'm going to call that as del S. To find the length of this PQ is very easy. You just look at the components that this PQ makes onto each individual axis, or you look at the projections of PQ onto X. So here we will have del X and projection of PQ onto Y. So here we will have del Y. So del S square is simply equal to del X square plus del Y square. This is the very obvious Pythagoras theorem that we are all familiar with. If you want to find out the length between 2 points in 2D space or in 3D space, simply use the Pythagoras theorem to get that particular length. Why? Because this is a right angle triangle, and in a right angle triangle, the length of the hypotenuse can be obtained by the length of the other two adjacent sides. Now, how is this different in space-time? So it is different in space-time in a very unique way and a very interesting way. So as opposed to xy coordinate system, if I have an xct coordinate system and I want to look at the distance between 2 points, let's suppose P and Q. So these 2 points may represent some physical events in space-time. So they will have some space coordinate as well as a time coordinate associated with them. Now, if I draw some kind of a line segment or a vector between P and Q, and I want to find out what is the length of this line segment, then we will have, as usual, the projection of this vector onto the x-axis, that will give me del x. The projection of this vector onto the ct axis, that will give me c del t, because c is a constant. However, in space-time, the distance del S between P and Q can be written by this expression del S square is equal to del X square minus C del t square. You see the minus here? This is the very interesting difference that arises when we calculate the distance between any two points in space time. This quantity, in fact, is a very important quantity because it is known as the space-time interval. I have talked at length about the space-time interval in one of my previous lectures where I showed how the space-time interval is invariant under a Lorentz transformation. That means if there are two separate observers moving at relative velocities and they are both measuring the distance between any two points P and Q, then they will measure the space-time interval to be exactly the same, and therefore the space-time interval becomes a very important quantity while describing physical events in space-time. So if you're interested in getting to know a little bit more about the space-time interval, you may want to check out my earlier lecture. Now, there are two conventions here. I get this question a lot. In some books, they use a negative sign before the space coordinate and a positive sign before the time coordinate. That is one possible convention. And in my case, I will be using a positive sign before the space coordinates and a negative sign before the time coordinates. This is also an equally valid convention. Both the conventions are quite valid, and as long as you maintain a consistency in your convention, your calculations are perfectly fine. So in some books, they use a positive sign before the space and negative sign before the time coordinates, and in some books, they use the vice versa. Now, one of the questions that arises very commonly is that why is there a negative sign here? Why is there a negative sign here as opposed to the positive sign when we measure the distance between 2 points in Euclidean space? Now, one very simple answer to this question is that the reason a negative sign arises between the space and the time coordinates in space-time is so as to keep the speed of light a constant. Let me explain that once more. There is a reason that the negative sign arises in space-time when we are trying to measure the distance between any 2 points in space-time, and the reason is quite simply to keep the speed of light constant for all observers. Now, you may recall the second postulate of special theory of relativity. What does the second postulate say? The second postulate said that the speed of light in vacuum is a constant for all observers. It doesn't matter if there is an observer at rest, it doesn't matter if there is another observer in relative motion, both of them, if they measure the speed of light, will measure it to be exactly the same. And it is a consequence of this simple statement that leads to a minus sign here. How? Well, this x and ct axis is with respect to some observer, right? There is an observer, according to him, he has the axis x and ct, but it's also possible to have another observer who is in relative motion with respect to x and ct, and he may be traveling with a particular velocity and he may have axis x dash and ct dash. Now let's do a very simple thought experiment. If the first observer who has axis x and ct tries to measure the speed of light, then he will see that a light photon travels a distance of, let's suppose, x in a time period of t, which will give him the speed of light, right? However, if the other observer who is traveling at certain velocities also tries to measure the speed of light, he will measure that the light photon travels a distance of x dash in a time period of t dash, so that the speed of light is a constant for him and the other observer. Do you see what's happening here? Measurements of time and measurements of space will sort of optimize in a manner to end up giving the speed of light constant for all observers. So for one observer, the distance traveled by a speed of light is x, but the time it takes is t, so that the speed itself is c. For another observer, the distance traveled by a photon is x dash in a time period t dash, so the speed itself is c. So both space and time measurements of various observers will be different, but they will optimize in such a manner so that their calculation of the speed of the light photon is exactly the same. And from here, I can conclude from this equation, I can simply say that x square upon t square is equal to c square. So I can say that x square is equal to c square t square, right? And from here also I can say that x dash square upon t dash square is equal to c square. So from here I can say that x dash square is equal to c square t dash square. Now from this and from this, if I construct the space-time interval, what do I usually get? So I will get that x square minus c square t square, x square minus c square t square is equal to how much? 0 from the first equation, right? But from the second equation, x dash square minus c square t dash square is also equal to 0. So you see what's happening here? The space-time interval for a light photon for one observer is this. The space-time interval for a light photon for another observer is this. So because of the second postulate of relativity, that the speed of light must be a constant for all observers, both of them will measure distances and time periods traveled by a light photon in such a manner that those distances and time periods will give a ratio for the speed of a light photon to be exactly c. And this is how the negative sign arises. That measurements of distances and measurements of time period for all observers will optimize in such a manner so as to keep the speed of light constant. This is why a negative sign arises here. I hope you have understood this very simple idea. Now, you may say that how is it possible that the space-time interval for a light photon is exactly 0? Well, this is because there is no limitation as to whether or not the space-time interval for any two events must be positive. Now, usually in Euclidean space, the distance between any two different points is always a positive quantity. This is always a positive quantity, right? However, because there's a negative sign here in Minkowski space-time, del S square can be positive, it can be negative, and for the unique case of a light photon, it can also be 0. This brings us to the next difference, which is null vectors versus light cones. So what is a null vector? In Euclidean space, if we construct a vector whose magnitude is 0, then we say it's a null vector. So for example, if I just draw a point in the origin, that's it. If I draw a point in the origin, then the position vector for that point is simply equal to 0 I cap plus 0 j cap, isn't it? This is a null vector. It has a magnitude which is exactly equal to 0. In fact, if I draw a line from one point to the very same point, then that vector will represent a null vector. However, because of the interesting difference of a negative sign here, when we measure the distance between any two points, in space-time, null vectors are those quantities or those line segments or those vectors in which del x is equal to del t multiplied by c. So for example, if I have a straight line that I draw, let's suppose I draw a straight line between x and t so that the changes in x and the changes in t happen in the same proportion. Okay, so if I draw a line like this, okay, and I take any two points here, if I take a point here and I take a point here, as you can see from the symmetry of this kind of a diagram, the del x and the c del t are equal to each other. So we'll have a del x and the c del t will be equal to each other. That means this vector, if I create a vector between these 2 points, is a null vector. Because what is the length of this null vector? What is the magnitude of this null vector? Well, because of the symmetry, del x is equal to c del t, or we can also say that del x square minus c del t square, or c square del t square, is equal to 0, which is actually the length of this particular vector, if I can call it, let's suppose, pq. So that means if I have this kind of a line at 45 degrees between the x and the ct axis, then any kind of a vector that I draw between any two random points, even if it may look like a straight line in my board, is actually in fact a null vector. And this null vector essentially corresponds to the motion of a light photon, as I have just now demonstrated before. Yes. So let me draw these two lines. So I have one line which is this, and there is another line to the negative x-axis, So any kind of a vector that I draw here will represent a null vector. This is given a very special name which is known as light cones. So you see right now I have a 2D diagram where we have the x-axis and the ct axis, right? What if I also include another axis which is the y-axis coming out of the board? In that case I will have an xy plane and the time axis going perpendicular to it. In that situation we will have not just two lines but a surface, a conical surface that looks something like this. And this conical surface will represent that surface in which if I draw 2 points, then the line connecting between those 2 points will have 0 magnitude. Therefore, the line will be a null vector. So essentially, it is the light photon that traces out a trajectory that represents a null vector. All right, let's move ahead to the next point. Now, again, we have the Euclidean space here. And if I want to draw a vector from the origin of the xy plane, let's suppose I have a vector like this, okay, I have a vector like this or a line segment here. Now let me ask you a question. What is the locus of all the points that is equidistant from the origin? All right. Or I can also say that what is the locus of all the points which are at the same distance as this particular point? The answer is very obvious. It is a circle. So if I draw a circle here, every point on this circle is equidistant from the origin. That means a vector from the origin to the circumference here or a vector from the origin to the circumference here, they are all equidistant. This is because the distance between the origin and any point on the circle is simply nothing but we can say as r. Okay, so what is r? R is given by r square is equal to x square plus y square. So the del will be removed because we are looking at the differences from the origin. So x square plus y square. This is nothing but the equation of a circle. The circle represents all the points which are equidistant from the origin in an Euclidean plane. All right. However, if I ask the same question in Minkowski space-time, what if I have a particular point here, all right, and I draw some kind of a vector to the point, what will be the nature of all the points which are equidistant from the origin? Or I can say, what will be the nature of the curve that represents all the points that are equidistant from the origin? Now, the distinction between the Euclidean space and space-time is that in Euclidean space, we have the Pythagoras theorem. In Minkowski space-time, we have the hyperbolic Pythagorean theorem, which is nothing but s square is equal to x square minus y square. So, in the hyperbolic Pythagorean theorem, we have, let's suppose here I am specifying the radius of the circle as r. Here let me specify it's not a radius of course, but the distance of the origin and the point as r square is equal to x square minus y square. There's a negative sign here. What is this equation? This is the equation of a hyperbola. So if I draw a hyperbola in this particular graph, what do I get? So we'll get something like this. We'll have these 4 hyperbolas corresponding to positive values of the interval and negative values of the interval. So that means if I draw a vector from here to here, now this has the same length in space-time as, let's suppose, a vector like this, as a vector like this, even though it looks in the diagram as if the line segments are shorter than the other, but in space-time. Okay, so here I am drawing the diagrams in space, but in space-time, all these line segments will have same length, as opposed to circle being the locus of all the points equidistant from the origin in Euclidean space. In Minkowski space-time, these hyperbolas constitute all the points which are equidistant from the origin. So if I choose some other point, for that we will have a different circle here. Right? And if I choose a different point, I'll have a different set of hyperbolas here. In fact, this will lead to one of the conclusions in point number 5 that I'm going to talk about. So in the fifth difference that I'm going to talk about Lorentz transformations and how Lorentz transformations are the hyperbolic rotations of space-time as opposed to simple rotations in Euclidean space. So this diagram will shed some light into that particular point also. Now, let us look at how the projections or the components of a vector are different in Euclidean space and Minkowski space-time. So the length of a vector in Euclidean space and the length of a vector in Minkowski space-time are different, right? But what about the projections? So let's suppose that I have a vector between any 2 points, between, let's suppose, O being the origin and P being any point here, okay? And the projections can be said to be from 0 to Q, or rather O to Q and O to R. Okay, let me take this particular angle as the angle phi. Let's take the same example. In space-time, we have this line OP that has a projection onto CT axis at point R and projection onto X axis at point Q, and this is the angle phi. Okay, now because Euclidean space and Minkowski space-time are slightly different constructions, and the nature of their constructions are revealed by the property of how we measure the distance between any 2 points, which is very different from one another, and therefore we end up these differences. The projections also follow a different property. For example, if I project OP onto the x-axis, if angle phi is this, then what is OQ? OQ is simply equal to OP sine phi. Yes or no? Very obvious. If I want to project OP onto the y-axis, then we will get OR. What is OR? OR is nothing but OP cos phi. Very simple. However, if I do the same thing here, if I project OP onto the x-axis, then we will get OQ, but OQ is simply equal to OP sine hyperbolic phi. So instead of sine phi, I'll have sine hyperbolic phi, and similarly if I project OP onto the time axis, we will get OR, and this will give me OP cos hyperbolic phi. So we'll have cos hyperbolic phi. So as opposed to in Euclidean space, where the projections of a vector can be written in terms of sine phi and cos phi, in Minkowski space-time, the projections of a vector onto the x and the CT axis are given by sine hyperbolic phi and cos hyperbolic phi. This is a very important distinction. In fact, using this, I can find out how the angles are related to the x and y, let's suppose, components. So for that, if I have, let's suppose, OR, or rather I say OQ upon OR. What is OQ upon OR? So OQ upon OR. OQ upon OR is nothing but tan phi, right? This is equal to tan phi. So which is equal to what? So tan phi, because OP sine phi upon OP cos phi is equal to tan phi. What is OQ? OQ is nothing but del x, right? What is OR? OR is nothing but del y. This is a very simple and very obvious calculation in the Euclidean space, that if you have a particular right angle triangle where phi is the angle, then tan phi is simply equal to the opposite side by the adjacent side, where the opposite side here is del x and the adjacent side here is del y. On the other hand, if I perform a similar calculation in Minkowski space-time, let's suppose I perform a similar calculation in Minkowski space-time, let's suppose I bring these calculations here, then I can say that OQ upon OR for space-time is equal to OP sine hyperbolic phi upon OP cos hyperbolic phi, which is nothing but tan hyperbolic phi, which is equal to how much? OQ is x, or del x, I can say, del x, and OR is how much? OR is nothing but del CT, or you can say C del T. So this gives us that tan hyperbolic phi is equal to del x upon c del t. This is a very important conclusion or very important difference between Euclidean space and Minkowski space-time. In Euclidean space, the projections onto the x and the y axis, their slope is given by tan phi, but in Minkowski space-time, the projections onto the x and the time axis, their slope is given by the tan hyperbolic phi. In fact, this can also give us an idea about the nature of the space-time with respect to a moving observer. So if I have in this frame of reference of x and ct some moving observer who is moving with constant velocity, then that observer will have a world line that is inclined to this x-axis and t-axis in this manner. So if this is the what we can say world line of an observer that is moving with constant velocity, then del x and del t will simply represent the distance that the moving observer travels in the time period of del t. So del x and del t will in that situation represent what I am going to call as the velocity of that moving observer upon c. So this brings me to my next point of how we can correlate two different observers in relative motion. So this is a space with respect to an observer, let's suppose in rest, who has x and ct axis. He is looking at an observer who is traveling at a particular constant velocity of v, and that observer has a world line in this OP slope, and that observer travels del x distance in del t time. So for him, v will be the velocity. So the space-time of that observer will be rotated or shifted by an angle phi such that tan hyperbolic phi is equal to v upon c. So this brings us to the last difference in this particular video, which is transformations of Euclidean space and transformations of Minkowski space-time. Okay, so in relativity, invariant quantities are very important. What is an invariant quantity? See, because distances are not absolute, time periods are not absolute, it becomes very important for us to figure out those quantities that will not change when we go from one frame of reference to another, that will remain invariant under a Lorentz transformation. So quantities that are invariant under a Lorentz transformation becomes very, very important to us because they retain their value even if we go from one frame of reference to another. Now, because in relativity that kind of a going from one frame of reference is known as Lorentz transformations, how can we visualize Lorentz transformations in space-time? Now, I already said that the space-time interval that we were talking about, x square minus y square, is invariant under a Lorentz transformation. So therefore, I want to figure out how would the Lorentz transformation look like in space-time and whether or not that quantity is invariant and what information can we obtain out of it. So therefore, I am going to ask a very simple question. What is the transformation of axis in Euclidean space that leaves the magnitude of a position vector invariant? What is the transformation of the axis in Euclidean space that leaves the magnitude of any kind of a vector invariant? And the answer is very simple. It is pure rotation. So if I have x-axis and y-axis, right, like this, and I have some kind of a vector, let's suppose I call this vector OA or OP, whatever. A transformation of the axis that involves pure rotation will leave the magnitude of the vector invariant. Yes? So if I have a vector in x, y, and I have the same vector in x dash, y dash, then the length of the vector in both x, y and x dash, y dash will be exactly the same. Therefore, the magnitude of the vector is invariant under a pure rotation. Quite simple, yes? Now, if I ask the same question but in space-time, what is the transformation of the axes in space-time that leaves a magnitude of a vector, or let's suppose some line segment and its magnitude OA, I call it invariant. So OA, what is its length? Its length is given by del x square minus c square del t square, right? As opposed to the length of a vector in Euclidean space, which is del x square plus del y square. In space-time, the length of a vector OA is given by del x square minus c square del t square. So what is the transformation of the axes that retains the value of del x square minus c square del t square? As it turns out, it is not pure rotation, but rather it is a rotation of the axes in opposite direction, something like this. As I have discussed in my previous lecture regarding Minkowski space-time, this is the visual representation of a Lorentz transformation in space-time that retains the length or the magnitude of a vector when we go from one frame of reference to another. So this is the visual representation of what happens in space-time when we go from one frame of reference onto another. What does it mean? It simply means that if x and ct is represented by some kind of an observer, and we have another observer, and I'm going to say that that observer is moving with some kind of a velocity v with respect to this observer, then the space-time axis for that observer will be x dash ct dash. Okay, now because this new observer, the orange observer, is traveling with a velocity of v with respect to the first observer, therefore he will have a world line like this. Okay, he will have a trajectory like this. Now I have discussed this extensively in my previous lecture also, where I took the example of Batman and Superman, if you remember, where the Batman, which is the observer in rest, has a time axis like this or a world line like this, and Superman, which is traveling at very high velocities with respect to Batman, has a world line like this. So the time axis of the Superman will look something like this, that subtends an angle phi, and from here, and based on the calculations that I showed previously, I can easily show that tan hyperbolic phi is equal to what? It is equal to del x upon c del t. What is del x upon del t? Del x is the distance traveled by the second observer in del t with respect to the first observer. So del x upon del t is nothing but the velocity of the second observer with respect to the first observer. So this is v upon c. So if we have two observers, one at rest, one in relative motion with velocity v compared to the first observer, then in the space-time diagram, the first observer will have x and ct axis, and the second observer will have x dash and ct dash axis, such that the angle subtended by the ct dash axis on the ct axis has a tan hyperbolic function given by v upon c. That is how they are related to one another diagrammatically in a space-time diagram. Now you may say, why is it that we have rotation that maintains the length of a vector in Euclidean space, but a similar transformation does not look like a rotation? The reason comes very simple if you think about it. If you think about it, both the observers must measure the velocity of light to be a constant. Now what is the velocity of the light? As I have discussed already, the velocity of light creates a world line that is a null vector. So it is a light cone. So both of them must measure the velocity of light to be exactly the same. So whether it is the first observer at rest or whether it is a second observer in relative motion, both of them will measure the speed of the light to be a constant or to be the same. And that is only possible if the x dash and the ct dash axis of the new observer is transformed in this particular manner, such that the angle subtended by the new time axis on the old time axis or the rest time axis is given according to this. Now visually, this is what the transformation of rotation and the transformation of Lorentz transformation looks like. But I want to go a little bit in detail. If you have stuck with me till this part of the video, I want to give a little bit of a bonus to you. What I'm going to do is, I'm going to mathematically obtain the transformation matrix corresponding to rotation and the transformation matrix corresponding to the Lorentz transformation. Shall we do that? Let's do that. So now you already know that rotation is the transformation that leaves the magnitude of a vector invariant in Euclidean space. So what happens in a rotation? So if I take the position vector, let's suppose of O, A. Okay, so if I take the position vector of OA, so OA, let's suppose its position vector is given by R in the original XY axis, but R dash in the new rotated axis. So even though it's the same vector and their lengths are same, but their components with respect to the new axes will be different. So for example, for the original set of axes, R will simply have x I cap plus y j cap, right? But in the new rotated axes, R dash will be equal to x dash I cap plus y dash j cap, I cap dash and j cap dash. So this is the same vector in the original xy axis, and this is the same vector in the rotated x dash y dash axis. Now if I multiply this equation with, let's suppose, I dash, let's suppose, okay, so if I multiply this, or I say I take a dot product, okay, that would be a more appropriate term. So if I take a dot product with I cap dash, then I'll have I cap dot I cap dash plus y j cap dot I cap dash is equal to x dash I cap dash dot I cap dash plus y dash j cap dash dot I cap dash. What is I dot I cap? So I dot I cap is nothing but, you have cos theta here. What is j dot I cap dash? This is nothing but, if you look at the diagram, j and I cap dash will give you a minus sine theta term here. What about I dash dot I cap dash? That is just equal to 0. And j dash dot I cap dash, that is also equal to 1. So this gives me x cos theta plus y, or rather I should say minus y sine theta is equal to x, or rather I have y dash here. Okay, I think I made a mistake here. The dot product between the I cap dot and I cap dot should be equal to 1 because the angle is 0, right? And here between j cap dot and I cap dot will be 0 because the angle is 90 degrees, right? So this will give us actually the x dash quantity. So this is the x dash quantity. Similarly, if I multiply the same equation with, or rather if I take the dot product with the j dash cap quantity, that will give me x sine theta plus y cos theta. You can try that out and see what you get. If I take the dot product of this particular equation with the j cap dash quantity, then this is the equation I get. So this, if I combine both of them, will give us the rotation of any vector quantity in Euclidean space. So if I write this properly, let me rub this one first and then I'll write it properly. X dash y dash is equal to cos theta minus sine theta and cos theta x y. So if I want to create a rotation of the axis in Euclidean space, this is the transformation equation. In fact, this matrix cos theta minus sine theta cos theta is the rotation matrix or the rotation operator. Performing this rotation matrix operator onto any given set of axes x and y essentially leads us to a rotated frame of x and y axis, which is the x dash y dash axis. Now I want to see a similar kind of a transformation equation for the Lorentz transformations. All right, for that let me rub the right hand side of the board. So here we have the Lorentz transformation. So the Lorentz transformations gives us an idea about how we connect the measurements of one observer to another observer. So you have t dash is equal to gamma t minus vx upon c square But since we are talking about Ct and Ct dash in the space-time diagram, I multiply with a C in this equation. So we get Ct dash is equal to gamma Ct minus V upon Cx. All right. Similarly, we have x dash is equal to gamma x minus V upon Ct. All right. Or rather, I should say V upon C into Ct. Okay. We have a Ct here. Y dash is equal to y, z dash is equal to z. I'm going to ignore these two equations. Why? Because I'm only going to look at the transformations for one-dimensional motion. Now these will simply give us 2 extra rows in the final matrix that we get. So 2 extra rows that contains 1 and 1 in the diagonal elements. So it's not going to be very important. So gamma, what is gamma here? Well, you already know that the gamma factor is equal to, gamma is equal to root over 1 minus v square upon c square. Right, or rather 1 upon root over 1 minus v square upon c square. What is v upon c? V upon c we have already obtained as how the new axis of the new observer gets slightly slanted by a particular angle phi, so that tan hyperbolic phi is equal to v upon c. So v upon c is tan hyperbolic phi. So from here I get 1 upon root over 1 minus tan hyperbolic phi whole square. So what is 1 minus tan hyperbolic phi square? That is actually, we can find that from the trigonometric expressions. That is nothing but root over sec hyperbolic phi whole square. So root over sec hyperbolic phi whole square is nothing but, 1 upon sec hyperbolic phi, and 1 upon sec hyperbolic phi is nothing but cos hyperbolic phi. So the gamma factor in the Lorentz transformations is related to this particular angle in the space-time diagram by gamma is equal to cos hyperbolic phi. So if I write down these two set of equations in terms or in this particular form, so now what do we get? So how does the Lorentz transformations look like? So the Lorentz transformation simply looks like Ct dash x dash is equal to, so here we have gamma minus v upon c gamma, and then here we have minus v upon c gamma, and we have x, or rather we have Ct and x. Okay, so what is gamma? Gamma is cos hyperbolic phi. What is minus v upon c? So minus v upon c is nothing but minus tan hyperbolic phi multiplied by gamma is cos hyperbolic phi. So here again we have the same thing, minus tan hyperbolic phi multiplied by cos hyperbolic phi, and here we have again cos hyperbolic phi, and this is Ct and x. So from here I can simply condense it. So tan hyperbolic phi is sin hyperbolic phi upon cos hyperbolic phi. So this cos hyperbolic phi and the cos hyperbolic phi, the denominator will cancel out, we'll be left with sin hyperbolic phi, and finally we have the transformation equations for Lorentz transformations. So Ct dash x dash is equal to, we have cos hyperbolic phi minus sin hyperbolic phi minus sin hyperbolic phi and cos hyperbolic phi Ctx. That's it. So this matrix represents the Lorentz transformation matrix. So this is the Lorentz transformation matrix operator, also known as Lorentz boost. So when we perform a Lorentz boost onto a given space-time axis, we end up getting a new set of space-time axis which represents the measurements made by a moving observer. So essentially, just like the rotation in Euclidean space preserves the length of a vector, a Lorentz transformation in space-time preserves the length of a vector. However, the rotation matrix in Euclidean space is given by this, but the Lorentz transformation in space-time is given by this. This, in a sense, is the Lorentz transformation. So the Lorentz transformation can be written in this way. connecting the measurements of two observers in space-time, but it also can be represented by the angle phi here. So angle phi simply tells us how the new space-time axes will be related to the original space-time axes of a rest observer. So if you have a rest observer and a moving observer meaning an observer traveling at a particular velocity with respect to the rest observer, their axes of x ct and x dash ct dash respectively will be related by this angle phi, and that gives us an idea about the essence of the Lorentz transformation. So these are some of the very simple differences between Euclidean space and Minkowski space-time. So we have discussed the Pythagoras theorem and hyperbolic Pythagorean theorem. We have discussed null vectors and light cones. We have discussed equidistant points representing circles in Euclidean space and hyperbolic curves in Minkowski space-time. We have also discussed the projections of a vector in Euclidean space and Minkowski space-time. And finally, I have shown how the Lorentz transformations are essentially the hyperbolic rotations of space-time. So this is all for today's lecture. In my coming lectures, I will use this kind of a space-time construction and the geometry associated with it to very simply derive some of the very important consequences of special relativity like time dilation, length contraction, velocity additions, etc., etc. So I'll see you in my coming lectures. That is all for today. Thank you very much.